September 14th, 2019. Port of Pevek, Russia, the most remote city in the Northern Hemisphere. A vessel 144 meters long slides into harbor. But this isn't carrying cargo. This isn't a military ship. This is something the world has never seen before operating commercially. A floating nuclear power plant with 2 full-scale reactors mounted on a barge, designed to power an entire Arctic city from the ocean. The engineering challenge? Build nuclear reactors that can survive ocean storms, Arctic temperatures down to -50 degrees Celsius, and potential collisions with ice flows, all while maintaining the same safety standards as land-based facilities. Oh, and make it movable. Because when the city's resources run out in decades, you need to tow your entire power grid to the next location. The Akademik Lomonosov represents one of the most audacious engineering projects in modern Russian history. And the question everyone asked when construction began in 2007 was simple: how do you make a nuclear reactor float? Today, you're going to find out exactly how Russian engineers solved problems that had never been tackled before. This is about the pure engineering brilliance required to put atomic power on water and make it work in one of Earth's harshest environments. To understand why Russia built this vessel, you need to understand the Pevek problem. Pevek sits at 69 degrees north latitude on the coast of the East Siberian Sea. Population, approximately 4,000 people. It's the northernmost city in Russia and one of the coldest inhabited places on Earth. Winter temperatures regularly hit -40 degrees Celsius. The port freezes solid for months every year. For decades, Pevek relied on the Bilibino nuclear power plant, located inland. Built in 1974, Bilibino used 4 small EGP-6 reactors that had exceeded their operational lifespan by 2015. They were scheduled for decommissioning. The problem facing Russian energy planners was brutal. How do you power remote Arctic settlements when traditional infrastructure is impossibly expensive? Building a new land-based nuclear plant in Pevek would cost billions. The foundation work alone would be a nightmare. Permafrost ground shifts constantly, requiring specialized deep foundations. Construction materials would need shipping during brief summer seasons. Construction timeline? At least a decade. But here's the real challenge. Arctic Russia is resource extraction territory. Mining operations, gas fields, and military installations are scattered across thousands of kilometers of coastline. These facilities need reliable power, but resources don't last forever. A mine operates for years, then exhausts its deposits. When that happens, settlements relocate. You can't build a multi-billion-dollar power plant for a temporary town. Russia needed mobile power. Power that could move when settlements moved. Power that could be built in a proper shipyard with quality control, then towed to wherever needed. Power that could serve one city today and a different city 20 years later. The solution was radical. Build the power plant on a ship. The idea of floating nuclear power wasn't new in 2007. The concept originated from a program that had been operating for over 50 years with remarkable safety records: nuclear submarines and icebreakers. The Soviet Union had been putting reactors on vessels since the 1950s. The first Soviet nuclear submarine, K-3 Leninsky-Komsomol, went to sea in 1958. By 2007, Russia had accumulated thousands of reactor years of operational experience with marine nuclear propulsion. The engineering knowledge existed.
Russian shipyards knew how to build reactor compartments that could withstand ocean conditions. They understood vibration dampening, corrosion resistance, and emergency cooling when surrounded by unlimited water. But submarine reactors were designed for propulsion and built for military purposes. They were compact, highly enriched designs optimized for power density, not electrical generation efficiency. What Russian engineers needed was a reactor optimized for civilian power generation that could survive the marine environment. The solution already existed in Russia's icebreaker fleet. Since 1959, the Soviet Union and Russia had operated nuclear-powered icebreakers, surface vessels with reactors designed specifically for electrical power generation. These ships regularly operated in Arctic conditions, survived ice impacts, and had accumulated decades of operational safety data. The reactor design chosen for Akademik Lomonosov was the KLT-40S, a modified version of the KLT-40 reactor that powered Russian icebreakers. Each reactor produced 35 megawatts of electrical power. 2 reactors would generate 70 megawatts total, enough to power a city of 100,000 people. But here's what made this different from icebreakers. The vessel wouldn't move under its own power. It would be a barge, a non-self-propelled floating platform. That changed everything about structural design, safety systems, and stability calculations. Because when a nuclear reactor can't maneuver away from danger, your engineering has to be absolutely bulletproof.
The construction contract went to Baltiyski Zavod shipyard in St. Petersburg in 2008 after initial work at Sevmash. The engineering team faced challenges that had never been tackled simultaneously before. Challenge 1. Build a structure that could support 2 complete nuclear reactor systems plus all supporting infrastructure while maintaining stability in ocean conditions. The final design was massive. Length 144 meters, width 30 meters, displacement 21,500 tons. The hull had to be deep enough for stability, but shallow enough to operate in Arctic coastal waters where deep ports don't exist. The hull design used double-bottom construction, 2 complete layers of steel separated by space. This provided redundancy. If the outer hull was breached, the inner hull would maintain watertight integrity. The space between could be monitored for leaks and serve as ballast tanks for stability adjustment. But here's the critical engineering problem. Nuclear reactors generate enormous heat. That heat must be continuously removed even when the reactor is shut down, because radioactive decay continues producing thermal energy. A land-based plant uses cooling towers or river water, but this vessel needed to operate in waters that freeze solid. The cooling system solution was elegant. Use the ocean itself as an unlimited heat sink, but engineer multiple redundant systems so ice formation could never block all cooling paths simultaneously. The primary cooling circuit used pressurized water flowing through the reactor core, heated to approximately 300 degrees Celsius, but kept liquid under high pressure. This superheated water transferred heat to a secondary circuit through steam generators, the same proven design used in Soviet marine reactors since the 1960s. The secondary circuit produced steam that drove turbine generators for electrical production. After passing through turbines, steam was condensed back to water in condensers cooled by ocean water drawn through hull intake ports. Here's where Arctic engineering brilliance appeared. The vessel had multiple separate seawater intake systems positioned at different hull locations and depths. If ice blocked intakes on one side, intakes on the opposite side continued functioning. If surface ice blocked shallow intakes, deeper intakes below the ice layer continued drawing water.
Additionally, the vessel carried emergency diesel generators, backup power systems that could run cooling pumps using fuel stored in protected tanks. These weren't small, portable generators. Each was massive, capable of running critical safety systems for extended periods without refueling. The reactor compartments themselves were engineering marvels of redundancy and containment. Each reactor sat inside a steel containment vessel designed to withstand significant internal pressure, enough to contain steam release from any conceivable cooling system failure. The containment vessels were then enclosed in secondary biological shielding made of steel and concrete construction. This provided both radiation shielding and structural protection against external impacts, collisions with ice, debris, or another vessel. But the most clever engineering solution addressed the fundamental vulnerability of any floating structure. What if it capsizes?
Naval architects face one nightmare scenario: a vessel rolling past its stability limit and capsizing. For a floating nuclear power plant, this is unthinkable. The engineering team needed to ensure that even in the worst possible Arctic storm, even with hull flooding, even with ice accumulation adding tons of topside weight, the vessel could not capsize. The solution involved ballast engineering at a level rarely seen outside military submarine design. Significant internal volume was dedicated to ballast tanks, compartments that could be filled with water to lower the center of gravity. These weren't simple tanks. They were sophisticated systems of interconnected compartments with pumps and valves allowing precise weight distribution adjustment. The vessel's stability calculations showed that even with flooding of multiple compartments, the center of gravity would remain low enough to prevent capsize. The buoyancy reserve, the amount of additional water the hull could take before sinking, exceeded requirements by substantial safety margins. But here's the engineering challenge that kept designers awake. What if the vessel broke loose from moorings during a storm and went adrift? The Akademik Lomonosov would be moored permanently in Pevek harbor. It wasn't designed for ocean transit under its own power. It had no propulsion system, minimal navigational capability, and no maneuvering ability. If mooring lines failed during a storm, the vessel would be helpless. The mooring system engineered for this scenario was extraordinary. Multiple separate mooring points connected to shore anchors designed to hold against enormous forces. The mooring lines themselves were heavy-duty steel cable with breaking strength far exceeding normal requirements, similar to cables used to anchor offshore oil platforms. But cables can fail. Ice pressure can shift anchors. The engineering team needed backups. The hull shape and weight distribution were designed so that even adrift, the vessel would naturally orient bow into waves, the most stable configuration. The flat bottom and deep draft created massive water resistance, preventing rapid drift. This engineering philosophy permeated the entire design. Assume everything will fail, then engineer backups that work anyway.
Construction began with keel laying in April 2007 at Sevmash Shipyard. The original completion date, 2010. The actual completion date, 2018. What happened during those 11 years reveals just how complex this engineering challenge really was. Initial construction at Sevmash proceeded, but in 2008, the project was transferred to Baltijski Zavod in St. Petersburg. By late 2008, the basic platform hull was taking shape. Then problems started. Problem 1. Reactor manufacturing delays. The KLT-40S reactors were being built by OKBM Afrikantov. These weren't production line items. Each reactor required custom fabrication of thousands of specialized components. Quality control was extreme.
Every weld was X-rayed, every pressure vessel tested beyond operational limits, every valve cycled thousands of times. The first reactor wasn't delivered until 2009. The second arrived in 2010. Problem 2. Baltijski Zavod faced financial difficulties in 2009. Construction halted for months while the facility reorganized. When work resumed, many specialized workers had moved to other projects. New crews required training on the unique requirements of reactor installation. Problem 3. Nobody had ever done this before. There was no instruction manual for installing nuclear reactors on a barge. Every step required engineering calculations, safety reviews, and regulatory approvals. The Russian Nuclear Regulatory Agency reviewed every system with extreme scrutiny. By 2012, both reactors were physically installed, but the vessel was perhaps 60% complete. All supporting systems, electrical distribution, control computers, cooling systems, crew facilities, still needed installation and integration. The work was slow because everything connected to everything else. You couldn't test electrical systems until generators were installed. You couldn't test cooling systems until electrical systems powered the pumps. You couldn't test reactors until absolutely everything else functioned perfectly. In 2015, a critical milestone, the vessel was floated out of the construction dock and moved to a fitting-out berth. This was the first time the hull floated with full reactor weight aboard. Naval architects watched nervously. The stability calculations proved correct. The vessel floated exactly as predicted. In 2016, the most critical testing phase began, reactor commissioning. This couldn't happen at the shipyard. Regulatory authorities wouldn't permit reactor testing near St. Petersburg's population. The vessel was towed to Murmansk, the Arctic port serving Russia's nuclear icebreaker fleet and Northern Fleet submarines. Here, at a facility with decades of nuclear handling experience, the real testing began. First reactor fuel loading occurred in late 2018. The fuel assemblies were transported in specialized containers and loaded into the reactor core through access ports. Each fuel assembly was checked multiple times before installation. Then came the moment of truth, bringing the reactor critical. In November 2018, control rods were slowly withdrawn from the first reactor core. As neutron-absorbing rods lifted, the neutron population began increasing. At precisely calculated positions, the reaction rate stabilized, criticality achieved. The reactor was alive. For months afterward, both reactors were tested through every possible operational scenario. Emergency shutdown tests, cooling system failure simulations, load variation tests, where electrical demand ramped rapidly. Every conceivable failure mode was simulated. Every test passed. The engineering worked.
In August 2019, the Akademik Lomonosov began its final journey, 5,000 kilometers across the Arctic Ocean to Pevek. But the vessel couldn't make this journey under its own power. It required towing by specialized tugs through some of the most dangerous waters on Earth. The nuclear reactors were shut down for transit. Operating reactors while being towed through ice fields was too risky. Instead, onboard diesel generators provided power for essential systems. The convoy included ice-breaking tugs that provided towing power and broke ice passages. The route followed Russia's Northern Sea Route, a shipping channel along the Siberian coast that remains partially frozen most of the year. The engineering challenge during transit was stability management. As the vessel moved through different water conditions, from Baltic seawater to Arctic saltwater to fresher coastal waters, density changed, affecting buoyancy. The ballast system required continuous adjustment to maintain proper trim and stability. The greatest danger was ice collision. Even with ice-breaking tugs clearing paths, large ice chunks could impact the hull. The double-bottom construction provided protection, but any significant hull breach could create stability problems. The journey, which departed on August 23rd, took approximately 3 weeks through some of the most challenging maritime conditions on Earth. After 22 days of transit, the convoy reached Pevek harbor in mid-September 2019. The vessel was carefully maneuvered to its permanent mooring location, a specially constructed berth with reinforced anchor points and underwater power cable connections to shore. Mooring lines were attached and tensioned. Underwater power cables, multiple redundant connections, were linked to the city's electrical grid. Shore-based control systems connected to the vessel's instrumentation. On September 14, 2019, both reactors were restarted and brought to full power. Generators began feeding electricity into Pevek's grid. The Akademik Lomonosov was officially operational. The vessel now provides 50 megawatts of electrical power and substantial thermal energy for heating, enough to power the entire city of Pevek and surrounding settlements. It replaced the aging Bilibino plant and the Chaunskaya thermal power station, which had been burning diesel fuel shipped in during brief summer supply windows.
The Akademik Lomonosov represents proof of concept that floating nuclear power plants are technically feasible. What makes this engineering achievement remarkable isn't just that it works, it's how the design solved problems that could have killed the entire project. Consider the operational record. The vessel has operated through Arctic winters where temperatures plunged below -40 Celsius and summers with constant daylight. It has survived storm systems and powered a city reliably while floating in water that freezes and thaws annually. The engineering solutions developed for this project are now being applied to second-generation designs. Russia's Rosatom has announced plans for additional floating plants using more powerful reactors. But here's what the engineering team considers their greatest achievement. They solved the mobile power problem for Arctic development. The Arctic contains significant undiscovered natural gas and oil reserves. Extracting these resources requires infrastructure in places where building permanent facilities is economically impossible. Floating nuclear power plants offer a solution. Move them in when extraction begins, move them out when resources deplete. The engineering applications extend beyond Arctic resource extraction. Island nations with limited land area but large coastal populations could use floating plants. Remote military bases could gain energy independence. Disaster response scenarios could benefit from mobile power generation positioned near coastal areas after natural disasters destroy land-based infrastructure. The vessel is designed for a 40-year operational lifespan. After approximately 12 years, reactors will require refueling. After roughly 24 years, major component overhaul will be necessary. At end of life, the entire vessel will be towed to a specialized facility for decommissioning. Perhaps the most important engineering validation, other nations are watching. China has begun construction of similar floating nuclear platforms. Several countries have expressed interest in the technology. The Akademik Lomonosov proved it could be done.
Today, the Akademik Lomonosov operates in Pevek harbor, generating power for 4,000 people who live in one of the most remote and challenging environments on Earth. But for engineers worldwide, it represents something more significant: proof that nuclear engineering can adapt to challenges previously considered impossible. The technical achievements are remarkable. The engineering team solved stability problems that would sink conventional vessels. They designed cooling systems that function in waters that freeze solid. They created containment structures that could survive collision or grounding while maintaining reactor safety. They built redundancy into every system so multiple failures would never cascade into catastrophe.
They did this by applying decades of marine nuclear experience from submarines and icebreakers, combining it with land-based reactor safety philosophy, and creating something entirely new. The Akademik Lomonosov isn't perfect. Critics legitimately question environmental risks of operating reactors in pristine Arctic waters. The economics remain debatable. The vessel cost approximately $740 million to build, which could have funded other power solutions. Strategic implications of mobile nuclear platforms raise questions about potential military applications. But from pure engineering perspective, this project represents human problem-solving at its finest. Designers, naval architects, nuclear engineers, and shipbuilders faced a challenge never solved before. Make atomic power mobile, make it safe, make it work in the Arctic. And they succeeded. For anyone who looks at a seemingly impossible challenge and wonders how you'd even begin solving it, this is your answer. You break problems into components. You apply proven technologies in new combinations. You engineer redundancy and safety margins exceeding requirements. You test relentlessly. You solve each subproblem until the impossible becomes merely difficult and the difficult becomes achievable. The floating nuclear power plant isn't science fiction. It's not a concept gathering dust. It's operating right now at 69 degrees north latitude in waters that freeze solid, powering a city in one of Earth's harshest environments. That's engineering brilliance. If you found this deep dive into nuclear marine engineering fascinating, subscribe because we explore these technical problem-solving stories every week. Next video, how Soviet engineers built an entire secret city underground at Arzamas 16 for nuclear weapons research, including constructing a metropolis housing tens of thousands without the outside world noticing. Hit subscribe and the bell icon. Drop a comment. What engineering challenge do you want explored next? Soviet submarine construction? Cold War radar innovations? Manhattan Project facilities engineering? Let me know, and I'll see you in the next one.